Uh, Hello, am I audible?
Yes, audible.
Yes, yes. Okay. Uh, okay. We'll start. Okay. This is the lecture series from the week number 6. Okay. Here we will discuss. I think I am audible to you all, and my screen is visible to you all. Is my screen visible?
Yes, sir.
Okay. 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 I am continuing. Uh, this is the whatever the week 5. Up to the week from the week number 1 to week 5, it was all about the hydrogen energy production. Okay. Next, just we'll start the storage method, and one by one we'll come forward, or we'll end up by studying the transportations and safety. Today we'll start the storage. Okay. The storage process, there are three major, three or four major different type of storage we'll study here. Three are the geological storage, and I mean physical storage, and one will be the mechanically compressing the hydrogen, compressing the hydrogen, compression hydrogen, compress on the compressed hydrogen store system. Okay. Okay. Just what is the basic property of hydrogen? Already we have studied in the first class. Okay. Whatever we discussed, that the diffusivity of hydrogen is very high. Okay. And viscosity of hydrogen is very low, lower viscous, and diffusivity is high viscosity, and very small molecules. Hydrogen is a very small molecule. The three term is very important. The three term, just I am writing the first term. The diffusivity is very high. Diffusivity is very high of hydrogen. Second is the viscosity. CITY, viscosity, viscosity. Third, viscosity is the very low actually. Viscosity is very low. Third is molecular size, molecule size, size of molecule, size of size is molecule is very low. as the diffusivity is very high, that means that means the storing systems or storing facilities or the storing process is very difficult to store this hydrogen, because you cannot you can't store for such a high diffusivity molecules, okay, gas molecules, because the diffusivity rate is very fast, okay. And the viscosity means that suppose water is flowing, adjacent layer resistance, okay, flowing resistance, that is the viscosity is very less, okay. That means the motion kinetics is very high, okay. That's why viscosity is very less, okay. And size of the molecule is also very small. Such a small hydrogen molecule, the storing of such a small hydrogen molecule is very difficult, because it can diffused through any small porous medium, okay. That's why the storing process is very difficult, okay. But why we will go for storing of hydrogen? We can directly we can use the hydrogen for different applications. Why the storing systems is important? Why we need the storing? Why? Do you know? Because no, just any one of you just answer me.
Yeah, storage is required. For example, we want to hydrogen for combustion, or we want to use the hydrogen as a fuel. So in that case, the compressed hydrogen would be required, because at higher pressure only the hydrogen can have the energy. So in terms
Oh,
of megajoule, just like
okay.
CNG.
All your answer is
I
very
think
correct. Hmm.
it is also required to meet the demand gap if the production is not there at
Exactly.
a time, and then you need.
Exactly. Exactly. Whatever why we are saving money? Because for the future purpose. Number one is the future purpose. One is the future purpose. When the energy will not be available in future, then the storage come into the function. Okay, for the future application. And second one is the demand and supply gap. Demand and supply gap. Demand and supply gap. Let me check whether the students are coming. Okay. Yes. Whatever we are discussing, that the demand and supply gap. Okay. The demand and supply gap. Second. And for demand and supply gap. That's why we need the storing of hydrogen. Okay. But in which parameter we are going to store, whether it is high compressed hydrogen or liquid hydrogen or atmospheric condition storing, that is the different part. But why the storage is required for the future application and demand supply gap, just to bridge the demand and supply, we record the storing process or storing application. But okay, but what is the main difficulties for storing of hydrogen? You can see that hydrogen has a very good calorific value. It has very good calorific value, means that the higher calorific value. Any other fuel, among all the fuel, only the hydrogen has so high calorific value, that is 120 megajoule per kg, means for 1 kg of hydrogen, from 1 kg of hydrogen you will get 120 megajoule of energy. In the case of LPG, only 46 megajoule of energy from 1 kg. Okay, but this 1 kg you can store, LPG you can store, just you can store in a small cylinder. In a small cylinder you can store this 1 kg of LPG. But hydrogen, for 1 kg of hydrogen, if you want to store at atmospheric conditions, it's required very larger container, like 5 storied building. This kinds of volume you required for 1 kg of hydrogen storing. Okay, that's the difficulties come, that's the challenges for storing the hydrogen. Okay, what is what the process of storing the hydrogen? Obviously we have to compress the hydrogen. Okay, we have to compress the hydrogen, but compression is also a difficult task for hydrogen compression. Okay, we required, we need compression 200 bar, 350 bar, 700 bar. Okay, these sort of high pressure we have to store the hydrogen at very high pressure, such that it will take a very small container or small area or small volume. Okay, for storing 1 kg of hydrogen. Okay, just you can see the some numerical value of hydrogen. Okay, hydrogen has a density of very small density. Okay, it is a very small density at in uh, normal temperature and pressure, I mean atmospheric conditions. The density is very less. When we are going to compress the hydrogen, the density will be high. Like suppose at 200 bar, the density is 15 kg, 15 kg per meter cube. Okay, whether the pressure is high at 350 bar, also the density is around 23.665 kg per meter cube. Okay, such that if we want to, if we go for higher compression, then the hydrogen density will also be high. Thus we can store the hydrogen for 1 kg of hydrogen in a small container. That's why we require very high compression ratio or very high compressed conditions. Okay, simultaneously all other the different fuel like methane, gasoline and diesel have the 32 megajoule per liter, 36 megajoule per liter for the diesel calorific value. Okay, we can store the hydrogen in a liquid conditions also. Okay, we can store the hydrogen in a high compressed gas conditions, and also we can compress the hydrogen, and we can change its state from the gaseous to liquid conditions. Okay, at 1 bar the calorific value like 8.5 megajoule per liter. Okay, and the density is like this, and we can store the hydrogen as a solid also, solid state also. Okay, the solid state, like its density 100 kg per meter cube. Okay, so far whatever we discussed, that hydrogen can be stored in a gaseous state, also it can stored in a liquid phase, also it can stored in solid phase also. Okay, this is the some basic storage of the hydrogen, or some basic properties of the hydrogen you have to remember. Okay, next just for example, suppose a motorbike or two wheeler, 1 kg, suppose let's consider 1 kg of hydrogen, 1 kg of hydrogen for a two wheeler, for your bike. 1 kg of hydrogen, it will go around 100 kilometers. Okay, for 5 kg of hydrogen, it will, the mileage will be 500 kilometers. Okay, but we have to design the your bike or two wheeler in such a way that at least at a time 500 kilometer it can run. For that we need 5 kg of hydrogen, but this 5 kg of hydrogen, the storing this 5 kg of hydrogen is very difficult because its density is very very less. Okay, it's require like at NTP conditions, at NTP condition, normal temperature and pressure conditions, the storage tank, the volume of storage tank should be around 11,940 liter. Is it possible to accommodate such a high volume of oil tank in your bike or a two wheeler? Is it possible? This is never possible to accommodate such a higher volume of tank such that your scooty or two wheeler or bike can run for 500 kilometer at a time if you refuel the hydrogen at a one time. Okay, that's why we have to do something. That's why the compression of the hydrogen is required. Okay, like 300 bar compressions, the volume of the tank is like 212 liter. Further compressions up to 700 bar, the volume of the tank is 125 liter. Further compression at 850 bar, but at higher compressions it is very difficult to compress at very high pressure. Okay, it is not easy to uh, compress hydrogen at 850 bar. What is the pressure of atmospheric pressure? Do you know what is the atmospheric pressure?
1.01325 bar.
Huh, almost 1 bar. Okay, 1 bar means 1 into 10 to the power 5 Pascal. Okay, this is a SI unit. Do you can you imagine that 1 bar pressure? I am living or you were sitting on your in your home under a pressure of 1 bar. Can you imagine that 850, 850? Can you imagine 850 bar pressure compression of hydrogen that require only 111 liter and 111 liter, 11 liter of tank. You have to accommodate 111 liter size tank in your two wheeler such that you can go 500 kilometer if you refuel hydrogen at one time. It is also not possible. That's why liquid hydrogen is possible. 75 liter somehow we can accommodate, or liquid hydrogen it can possible. That's why the aerospace industry they uses liquid hydrogen for the uh, rocket propulsion. Okay, or solid hydrogen, they also the solid hydrogen. Nowadays the scientists are using the solid hydrogen, 33.3 liter volume tank. Okay, solid hydrogen, this is the thing, but it depends on the applications actually. Okay, for the movable application, for the movable automobile industry, it is very difficult to use the hydrogen as a fuel. Also, if we use the hydrogen as a fuel, direct fuel, the efficiency is very very less. But indirectly, if we use the hydrogen, already I discussed in the first class, the if I use the indirectly hydrogen like intermediate case fuel cell, through the fuel cell, the efficiency is very very good. Okay, up till date, the hydrogen fuel cell can be used as a intermediate for the energy conversions. Okay, otherwise directly hydrogen fed car is very difficult or not viable till now. Okay, further research is needed. Next, the history of hydrogen storage. I will not go into details the hydrogen history of hydrogen storage. Okay, these are the different applications, space and military applications. Okay, you can see the phase diagram already I have discussed, or you can study it from the previous classes. But whatever, just I want to mention that, okay, just I am choosing one different color. This is the triple point and critical point. This is the critical point. This is the critical point, and this is the triple point. Already I discussed. You know the what is the characteristics of the critical point and what is the characteristics of the triple point. But here, whatever I want to mention, you have to remember or you should know that the hydrogen, metal hydrogen, solid hydrogen, you know, okay, gas hydrogen, you know, this is the metal hydrogen. Metal hydrogen means temperature is very temperature is less. Temperature is less means up to this temperature is less. This is the temperature is less. Whether when we will go in left hand direction, the temperature is less. Temperature is less and pressure is above 10 to the power 6 bar. 10 to the power 6 bar. This behaves like metal. Okay. So we can call it metal hydrogen. Okay. This is the things. Metallic hydrogen. Okay. You can see the properties of the metallic hydrogen here. Okay. And plasma hydrogen, obviously the temperature should be high. Plasma hydrogen. This exists in the solar system. So sun. Okay. Plasma hydrogen. Plasma is a ionic phase. Okay. Plasma hydrogen. Metallic hydrogen at very low temperature, at very high pressure. That is the metallic hydrogen. Okay. Temperature is low. This is the thing. Okay. You should remember. You should not confused with the metal hydrogen. Suppose I am asking you the questions: what is the metal hydrogen, and what is the minimum pressure? What is the critical pressure of the metal hydrogen? Okay, you should say the pressure should be above 10 to the power 6 bar. Okay. Next is the compressibility factor. Compressibility factor. Compressibility factor. Why the compressibility factor comes? Okay. Before coming to the compressibility factor, we will discuss the equations of state. Okay. For any thermodynamic systems, temperature, pressure, and volume, you can define the thermodynamic state, or any gas or any liquid, you can define its state by using its temperature, pressure, and volume. Suppose I am telling you that I have 1 liter hydrogen that has a 1 liter hydrogen that has a volume of uh, suppose 10,000, 10,000, suppose longer. This is the meter cube. This is not writing. This is the meter cube. This is the liter. Sorry, this is the suppose liter volume. I mean V, and this is temperature. Suppose temperature is 298. Temperature 298. Temperature 298 Kelvin. This is the temperature, and this is the volume. This is the volume, and this is the pressure. Pressure is the 1 bar. 1 bar. When we when you mention temperature, pressure, and volume, then only we can say its thermodynamic state or any state of the matter. Okay, you should mention the temperature, pressure, and volume. This is very important actually. Okay, Also, you can mention one thermodynamic systems in terms of calorific value or calorific equations U, T, V or HTP, internal heat, temperature, volume, or enthalpy, temperature and pressure. And also you can define by saying its entropy, temperature and pressure. These are the way of expressing the thermodynamic state. Okay, these are the way of expressing the any system or thermodynamic systems. Okay, the compressibility factor comes. Okay, this is the Van der Waals equation. This is the Van der Waals introduction. The compressibility factor comes. Why the compressibility factor comes? Because whatever we have studied, this is the ideal gas equation. This is the ideal gas condition. Okay, but in the real condition, there should be, or you have to incorporate the one term, that is the compressibility factor. Z is the compressibility factor because Z determines the difference between the real and ideal gas condition or real and ideal gas state. Okay, so what is Z? Z is the compressibility factor. Z is the compressibility factor, like PV equals to nRT. In place of nRT, when nRT, that means when PV equals to nRT, PV equals to nRT. This is the ideal gas equation. Ideal gas equation, but in our practical case, PV equals to nZRT. Z is one factor. This is the real gas. This is the real gas equation. Z is the factor. It can differentiate how much different, how much different, how the gases is different, how much the gas is different from the ideal gas condition. Okay, this is the Z. Okay, it can be determined by the n ideal by n real and m ideal by m real. Okay, already this is also I have discussed. Okay, the normal hydrogen is a mixture of ortho, 75% ortho and 25% para. 25% para. 25% para. Okay, but the conversion is important from the ortho to para. From the ortho hydrogen to para hydrogen, which one is the most stable hydrogen, stable condition? The para hydrogen is more stable condition. The stable conditions means that it has a lower energy state, low energy state, low energy state, low energy state, most stable. Okay, low energy state, when the conversion from the ortho to para hydrogen, the conversion from the ortho to para hydrogen, some energy or heat energy will released. This some sort of heat energy is released, and it is like exothermic process. The energy is released, and this energy during the conversion from the ortho to para, this higher amount of the heat can make explosions of the hydrogen. Okay, so during the conversion from the ortho to para hydrogen, you should remove, or you should remove the heat from the systems. Okay, this you have to remember. And one thing you have to also remember, that the inversion temperature is also important. Okay, the above the 193 Kelvin temperature, the Joule Thomson coefficient 193 Kelvin, 193 Kelvin, the Joule Thomson coefficient is positive. Okay, okay. That means, okay, and below this it is negative. Okay, this is very important for the whether the heat is generating, whether the heat is releasing, whether the heat is generating or whether the heat is absorbing. Okay, the hydrogen. That's why this Joule thermal coefficient is important. We will see this Joule thermal coefficient by the using this equation actually. Hydrogen storage method, physical method, and compressed hydrogen we can store, liquid hydrogen and adsorption hydrogen also we can store. There is also some chemical storage also, like metal hydride, means at the uh, CuH. That means that the hydrogen is storage. Hydrogen is metal hydride form, in the hydride form. Okay, ferrous hydride FeH. Okay, chemical hydride. Okay, in the hydride form, the hydrogen is stored. Okay, metal hydride, chemical hydride, and LOH, that is the liquid organic hydrogen hydrocarbon. Okay, this is the three different methods for chemical storage. I am not going into details. This is some parameter, the storage parameter. Already the international standard they have fixed this parameter. This should be there for storing the hydrogen. Okay, or the using the hydrogen, for using the hydrogen as a fuel. This is the some parameter. Okay, just parameter like that, the gravimetric capacity, gravimetric capacity, gravimetric capacity. Okay, that means that per kg how much energy, kilowatt hour per kg, it is now 1.8. I mean around the target is up to 2025. The target is 1.8 kilowatt per kg, but ultimate target means final target is 2.2. Okay, that means the higher. And the similarly hydrogen system volumetric capacity, the volumetric capacity is target is also at 2025 1.3, and ultimate target is 1.7. This is the things you can remember, or you can see, or you can study. Next is the hydrogen storage for the underground hydrogen storage. Okay, this is the history of the underground hydrogen storage. Okay, just you will go through the modifications or research modifications, uh, or the innovations is done year by year. You can go through. What is the advantages of the hydrogen storage, underground hydrogen storage advantages? Underground hydrogen storage means that the hydrogen will be stored at below the earth crust. Okay, I mean above the, it's not above the earth, it's below the earth crust or underground. Okay, why this underground hydrogen storage is required? Why the underground hydrogen storage is required? Any one of you? because because underground hydrogen storage has one advantages that it will not easily come into contact of the atmosphere or atmospheric oxygen. Sometimes what happen, the hydrogen is a very high explosive gas. If it come into contact with oxygen, it can be explosive. Okay, that's why hydrogen may be preferred. Hydrogen storage may be preferred at underground condition. Some of the advantages like that long term large scale storage, hydrogen can be stored at underground conditions very large amount or very large scale. Okay, and it is very economical also. Okay, how it is economical we will see. Okay, and it is very proven technology, and it has a very good performance and less microbial contamination, and it is very safe. Overall it is very safe. What are the disadvantages? The integration challenges is very difficult. Like integration challenges means that the constructions of this type of oil or constructions of this type of underground storage systems is very difficult. The high purity of the hydrogen is difficult to get the high purity of the hydrogen because it involves several injections of the hydrogen steps and the removal of the hydrogen or taking of the hydrogen from the hydrogen storage. That's why the contamination, the purity is a issue. Okay, also it can mix with the other gases present inside the or below the earth crust, the storage places, and the availability of such a geological structure is difficult to get. Okay, there has some certain type of structure. Hydrogen cannot be stored at anywhere of the earth crust. It has some parameter or it has some properties. According to this property or parameter, hydrogen can be stored, and monitor the safe and proper regulatory framework is required. This is simple. I am not going into detail. The property of hydrogen you have already studied: less density, less viscosity, high mobility, better efficiency toward withdrawal. Okay, lower coning means that the less viscosity. Okay, that's why these are the advantages or these are the properties of the hydrogen. That's why we are going to store the hydrogen in underground storage condition. Okay, because lower coning is very good when we will remove the hydrogen or when we will store the hydrogen or when we will put the hydrogen through a pipe. Okay, then if the lower viscosity, then the lower energy required to flow the hydrogen from the one place to another places, or uh, to go to put the hydrogen inside the earth crust, it is easy. Okay, that's why some hydrogen has some advantages for storing at underground conditions. Underground storage, rather than the hydrogen, except hydrogen, the carbon dioxide also can be stored, town gas also can be stored, methane also can be stored, the hydrogen also can be stored. Okay, hydrogen can be stored in porous media all or cavern based storage. Okay, just I am explaining something, that is the salt cavern hydrogen storage. What is the salt cavern hydrogen storage? It is very important. Salt cavern hydrogen storage. Anyone of you know how the salt cavern hydrogen storage work, or what is the working step of salt cavern hydrogen storage? Okay, we know that earth crust is a combinations of the different layer. Okay, clay layer, upper side clay layer, and below the clay layer it has different salt layer or different rock layer. Okay, just below the rock layer there are somewhere, in some places there are salt present in between the rock. There are salt present in between the rock, not the whole places, but some places. First, what we will do? Drilling. One is the drilling. We will drill. We will drill through the drill bit. We will drill. Okay. The engineers drill through rock layer to reach the salt dome. Salt dome means the salt layer. Okay. Then the leaching of this salt and water. Then we will drill and then we will put the fresh water into this salt, and it will make salty water, like salt plus water, and this when then we will extract this salty water outside from the well, or thus we can make one storage system for the hydrogen. Okay, at underground conditions, and we will put one pipe, and by through the pipe, after storing the, we can get back hydrogen. Okay, then the hydrogen injection, and after then when we require the compressed hydrogen or hydrogen, we can uh, receive from this salt cavern storage. Okay, these are the, and in the salt cavern storage the hydrogen can be stored at a very high compressed condition. Okay, these are the all things you can study. Okay, whatever I discussed. Okay, and next is the aquifer. What is the aquifer? Aquifers, any one of you? What is the aquifer? Aquifers is a very interesting thing, that there are some layer, there are some rock layer, porous rock layer. This is suppose porous rock layer. This is porous rock layer. Okay, porous rock layer means that the porous means it has also water molecules inside it. Okay, if we drill, if we drill up to a porous rock layer, it lies 200 500 meter to 500 meter to 200 2000 meter below the earth surface. Okay, there are some porous rock surface presents. In this porous rock surface the water molecules adhere into the surface. If we drill up to this layer, I mean up to 2000 meter below the earth surface, and we can push some gases at high pressure. Okay, then what will happen? The water will go side, water will go side by side. Okay, this is the water, this is the water, and it will create some vacuum, it will create some vacuum. This is the vacuum place, this is the vacuum place. Okay, and this porous vacuum place or porous stone can absorb the hydrogen at a very high pressure. Then according to our requirement we can get this hydrogen back for the further use or further applications. This is the aquifer. Just you go through this aquifer. Okay. Then coming to the depleted oil and gas reservoir. Depleted oil and gas reservoir means that uh, somehow the somewhere in the earth surface many years back there were presence of oil or gas or natural gas or coal. Okay. And it has already mined means it has already used, we have already used. Okay. So this portion is vacuum. Okay, this portion is vacuum. This vacuum portions can be used for the hydrogen gas storage. Okay, it has some advantages, has some disadvantages. Like there are oil or gas previously present, that this oil and gas can react with the hydrogen. Okay, and when we get back this hydrogen, this oil and gas mixture of the hydrogen we can get. Okay, that's why we cannot get the purity of the hydrogen or high purity of the hydrogen gas. Okay, this is the disadvantage of the depleted oil and gas reservoir conditions. Just you read, a depleted reservoir can be defined as a reservoir in subsurface. Subsurface means at the underground sand or rock formations that has previously produced oil and gas and is used for storing natural gas. Okay, natural gas means that the hydrogen, methane. Okay, there are three different type of underground reservoir, namely depleted gas reservoir, aquifer, and the salt caverns reservoir. Okay, these are the three different type of the underground hydrogen storage you have to study. Okay, and you have to study the advantages and disadvantages of this three different type of underground storage systems. This is a worldwide underground hydrogen storage project you can follow. Okay, and you can see the working conditions, the pressure of this site, 45 bar, 70 to 137 bar. Okay, the highest pressure they have attained, uh, 82, sorry, 68 to 200 bar. This is in USA. Spindle top. Okay, this is also salt dome. Okay, this is also salt dome. This is now operating conditions. Okay, the pressure is very important. At how much pressure I am storing the hydrogen at underground conditions. Okay, this is the easy things you can go through. Okay, next I am coming for some basic thermodynamics. Let's see, someone is uh, trying to join. Okay, okay. Uh, we will see some basic thermodynamics for the hydrogen compression, because we will use this term for the hydrogen compression process or hydrogen compression method. Isobaric conditions. This is the isobaric conditions. What is isobaric conditions? Isobaric conditions means the pressure is constant. This is the PV diagram. Okay, the pressure at 1 and pressure is 2 is same. That means P1 equals to P2. When the system has a pressure, initial pressure and final pressure is the same, then it is called isobaric pressure. Okay, the work done of the isobaric pressure, okay, work done of the isobaric pressure is P into V. V means that the delta V, change of volume, pressure multiply change of volume. This is the work done. Why we are going to study the work done? Work done is very important, because for compressing hydrogen you have to put some effort in terms of work done. Okay, you cannot do, you cannot compress the hydrogen without any work done. So you have to do some work done for compressing the hydrogen. That's why this basic thermodynamic process is important. You should understand this process. And isochoric process, isochoric process means that the volume is constant. Initially isobaric, isobaric means bar, bar matlab pressure, P is constant. This is the P is constant. P is constant. Achha, let me change the nib actually. 1 minute. Okay. Next is the isochoric process, means that volume is constant, volume is constant, and pressure is from pressure is P1 and P2. Okay. In this condition, what is the work done? In this condition, the work done is zero. Work done is zero. And from the thermodynamics first law, you can see that the Q equals to change of the internal energy. This is the things. We are not going into details, but we are interested in the work done. Okay. Next is the isothermal process. Next is the isothermal process. Isothermal process, that process that the temperature remains constant. The temperature is constant. T equals to constant. That means that the initial temperature and final temperature is constant. What is the PV curve? PV curve is like this curve. Okay. Uh, we will see the temperature isothermal process work done in next. Like isothermal process work done equals to Q. Okay. From the thermodynamics first law, okay, Q equals to del U plus W. Here internal energy is dependent on temperature. As the temperature change of temperature, as the change of temperature is zero, so internal energy is also zero. So Q equals to work done. If you can find the value of Q, this Q is equals to W or work done. Okay. In the adiabatic condition, adiabatic means there are the no heat, no heat exchange. Okay. No heat added or no heat released from the systems. This is called adiabatic condition. That means delta Q equals to 0 from the thermodynamics first law, that delta U equals to minus W. Okay. The change of internal energy equals to its work done. Okay. Change of internal energy equals to its work done in the case of the adiabatic conditions. Okay. One question I would ask you, that what is the difference between, what is the difference between isentropic process and adiabatic process? Isentropic process and adiabatic process. One thing you know, that isentropic process means that the change of change of entropy change of entropy or ds delta s equals to 0. Okay, an adiabatic process, there the change of heat dq equals to 0, means there are no change of heat energy, dq equals to 0. Okay, but sometimes we, for the reversible conditions, for the irreversible conditions, what is the main thing? For the reversible conditions, do you know the reversible condition? Reversible conditions means that any one of you, do you know the reversible conditions? What is the reversible conditions in thermodynamics and what is the irreversible conditions of the thermodynamics? Reversible and irreversible. Reversible and irreversible. The reversible conditions means the change of state, the change of state, we can initial state, suppose this is the initial state, suppose this is initial state 1 and final state 2, we can reverse the state from 1 to 2 or 2 to 1. This is the reversible. This is not easy actually, just I am explaining. Irreversible condition means that you cannot go back its initial state, that is the irreversible is happening. How the reversible, for achieving the reversible state, it is very difficult. Infinitely smelly small changes should be there, then only the reversible conditions will appear. Okay, anyhow, uh, sometimes the isentropic conditions and adiabatic conditions is same, or for the adiabatic conditions, for the irreversible adiabatic, for the reversible adiabatic conditions, we can say that the delta for the irreversible, for the reversible, for reversible, for the reversible adiabatic process, adiabatic process, we can write, we can write delta s equals to 0. Also we can write delta q equals to 0 or dq equals to 0. Am I correct? But irreversible adiabatic case, you cannot, but irreversible adiabatic, for the irreversible adiabatic you cannot write, for the adiabatic case you can write dq equals to 0, but you cannot write delta s equals to 0. What is the thing, or what is the importance of reversible? Just you see the formula, ds equals to dq by t plus entropy generations for the process. This is the, whether the process is reversible, whether the process is reversible, h generations is 0, h generations is 0, and ds will be dq by t, ds will be dq by t. For the, for adiabatic process, this is the reversible process, this is the reversible process. Coming to the adiabatic process, reversible adiabatic process, dk equals to 0, so ds equals to 0. So reversible adiabatic process, ds and dq both are 0. But for the irreversible case, the h generation is not 0. Okay, it is obviously greater than 0. For the irreversible, the entropy is always higher, or entropy generations or entropy is more than 1, more than 0. So So for the irreversible case, the equations is like this: ds equals to dq by t plus s generation, and for the isentropic condition, this is the irreversible isentropic. This is the irreversible isentropic process. Isentropic process ds equals to 0. So dq by t equals to minus s generation. Okay. So dq equals to t into s generation. Okay. So this is irreversible isentropic process. Irreversible isentropic process ds equals to 0, but this is not dq equals to 0, but dq has some value. dq equals to not 0, so dq has a value that it is multiply temperature with minus of s generations. This is the most interesting part of the thermodynamics. uh, Next is the Joule-Thomson effect. Okay, Joule-Thomson effect is also important. Joule-Thomson effect comes for the hydrogen or gas expansion process. Okay, gas expansion process. This Joule-Thomson process can be calculated. This is the function of temperature and pressure, and this can be written as delta T by delta P at constant enthalpy. This H is representing the constant enthalpy. Okay, and Joule-Thomson effect, there is a change of temperature. Okay, temperature may be high, temperature may be low. This is one important formula. This is very important thing. Sometimes these questions will come into your competitive examinations also. Okay, this questions is very important for GATE, graduate aptitude test in engineering. Okay, or the Joule-Thomson effect. Joule-Thomson is positive, negative. Okay, and temperature is less than 0, greater than 0. Okay, and how the temperature is calculated, this formula delta T equals to T is a function of enthalpy and pressure, and minus T1, it also temperature and pressure. Okay, but pressure is changing. Okay, but enthalpy is same at constant enthalpy. So pressure is changing, so we can change in temperature can calculate it from the pressure P1 to pressure P2. Joule-Thomson efficiency, Joule-Thomson coefficient into dP. Joule-Thomson coefficient itself is a function of temperature and pressure. Okay, you can calculate the delta T or T1 minus T2. You can find if the initial temperature is given to you, you can find the final temperature from by using this equation. Okay, and for the real gas equations, the Joule-Thomson is positive. If the Joule-Thomson is positive, the gas is cooled down. Okay, the gas is cooled down. That means the temperature is uh, reducing. Okay, for the isenthalpic expansion process. Suppose for the expansion process, the Joule-Thomson process is positive, then the gas is cooling down. Okay, the gas temperature is lowered. The gas temperature will be lowering. Okay, but this is just opposite. If the Joule-Thomson temperature is negative, okay, it will heat up. Okay, and next is the ideal gas equations and real gas equations. This is important for the equations of state. Ideal gas equations, PV equals to MRT or nRT. Okay, PV pressure, volume, mass, and gas constant. This is the temperature. N is the molar mass, and R is the characteristics gas constant. Okay, this is the specific gas constant, and this is the characteristics gas constant. Okay, and this is the T is the temperature. Okay. Okay, these things is also important actually. You can find out H enthalpy. Enthalpy is a function of T. How you can find out the enthalpy? Okay, for the ideal gas equation, if you integrate from the initial temperature to final temperature, the Cp, specific heat at constant pressure, multiply delta T, okay, and the U, U means internal energy, it also is a function of T. It is also determined by using the specific heat at constant volume multiply dt. The temperature, it is also a function of temperature. That's why we are integrating from the initial temperature to final temperature, and it is a function of U internal energy is a function of internal energy. It is important actually. Internal energy, ENER, internal energy is a function of CV, specific heat at constant volume and temperature. Okay, that's why in initial case, whether the at constant temperature isothermal process, the internal energy is 0. Delta T equals to 0. Internal energy delta U equals to 0. Okay, because the equation from this equation you can see. Okay, one thing I forget, but this is the all the equations for the ideal gas conditions, but real gas conditions you have to put one extra term or factor, that is the compressibility factor. This is the Z is the compressibility factor. Okay, Z is the compressibility factor. The all the things are same, PV equals to MRT IRT, but Z is the compressibility factor you have to include for the real gas situation. What is the difference between the real gas and ideal gas? Do you know? What is the difference between the real gas and ideal gas? Real gas, difference between real gas and ideal gas. Ideal gas. For the real gas, the gas molecules is considered as a sphere and solid sphere. But the real gas, solid and ideal, solid and concrete, solid and spherical size of the gas molecule. But for the ideal gas, it is not like this. For the real gas, two solid sphere or gas molecule, when they collisions, okay, it is not elastic collision, but ideal gas conditions it is elastically collisions. Elastically collisions means that the deformations will be there for the ideal gas condition. But ideal gas conditions, but for any calculations or any fundamental study, we will consider any systems as a ideal gas, then we will go into details like considering the real gas factor. Okay, this is the curve density versus pressure, you can see. Okay, this is the linear curve, because this is the linear variation. Okay, at different temperature and different uh, real gas and real van der Waal gas and real Z factor and ideal gas. Okay, and isentropic exponent is like this, PV equals to K equals to constant, PV equals to V to the power K into P to the power 1 minus K equals to constant. These are the different equations. These are the different equations are used for the ideal gas conditions. 1, 2, 3 equations. But for the real gas equation, PV equals to Z MRT. Okay, but here PV equals to constant PV to the power K, PV equals to V to the power K2 into P to the power 1 minus K2 is constant. These three equations are used for the real gas equation. And for the real gas conditions, this is important. This is the real gas constant P V to the power K 1 by taking one equation. Okay, P to the power P into V to the power K1 equals to constant by using first equation. This is for the real gas. This is for the real gas. That means Z should be there, or Z compressibility factor have come into the equation. That's why if you calculate the temperature relationships T2 divided by T1 equals to Z2 divided by Z1 multiply the pressure ratio to the power K1 minus 1 divided by K1, and K is itself depend on the temperature and pressure also. This I think already you have studied in the thermodynamics or chemistry in your 12th classes. Okay, these things you know. In what are the different compression process, we are interested for calculating the work done for the hydrogen. There are two different basically broadly two different compression process: isothermal compression process and isentropic compression process. Isothermal compression process means that the temperature is constant, and isentropic compression process means that the entropy is constant. Okay, and you have to remember that isothermal compression process work done is minimum work done required for the compressions, but the isentropic compressions the work done is higher theoretically for the ideal situation. And for the single and multi-stage compressions, it is considered that it is isothermal compression process, and no cooling, moderate pressure ratio, it is considered as the isentropic compression, isentropic compressions. In practical case, there are multi-stage compression process, because when you compress the hydrogen, by using one piston cylinder, the temperature of the hydrogen is increased. If the temperature is very high, it can be explosive. Before explosion, you have to reduce the temperature or by arranging some cooling jacket, okay, such that the temperature will not increase. The temperature will not increase, that means isothermal process. Okay, also we know that the in isothermal process work done is minimum. Suppose I am giving two options, that you required hydrogen from 2 bar hydrogen to 700 bar hydrogen, 700 bar hydrogen. Okay, in which process you will go, whether you will go for the isothermal process, isothermal isothermal process, or you will go for the isentropic process. Which option will be right?
Better to go with isothermal.
Yeah, better to go with
Isothermal,
the
yeah.
isothermal process, because it requires.
Only, sir, there is one confusion in terms of see the work done, whether it would be positive or negative. We are doing work on the system. In
Yeah, exactly.
compressor,
Yeah, I am discussing. Okay, better to go with the isothermal process because for the work done, why for the work done there are minimum energy required than the isentropic process. Okay, work done. Suppose one system, suppose one systems. I'm taking different color, black color, dark blue. Suppose I am taking one systems or one piston cylinder. It will be better for understanding. Suppose one piston cylinder. This is piston cylinder arrangement. Okay, good questions. This is also some basic questions you have to understand. Otherwise, it will be difficult. This is the gas. This is the hydrogen gas molecule inside the cylinder. This is the piston. This is the cylinder. Okay. When the pistons will move downward direction, the hydrogen gas will be compressed. The piston is moving downward direction. That means some work you have to put. Okay. The piston cannot itself uh, come from the upward to downward direction. You have to press, you have to put some force here, you have to put some force. Okay, that's why the piston will come downward directions and hydrogen gas will be compressed. Here I am giving some work to the system, I am giving some work to the system. Is it clear? I am giving some work to the systems for getting compressed hydrogen. Okay, so one systems, this is one systems, I am giving some work to the systems, I am giving some work to the systems, and the some heat, I am giving some work, work, and some heat is releasing, the heat is coming out. Okay, actually when you will compress the hydrogen, some heat will generated or temperature will be high, that means the heat will coming out. This is the output. Okay, when the work is input to the systems and heat is out. Okay, what is the positive negative? Positive negative term is not actually important, you have to realize the exact scenarios. Okay, but some books they mention that the when the work will be done by the when the work will be done by the systems, that is the positive. Work will be done by the systems, here the work is not done by the systems, here I am giving the work, the systems is giving the energy. Okay, some books they mention that work is done by the system, work done, work done, done, done by system, by system, system, work done by systems positive. Okay, and heat, work done by systems is positive, and heat input to the systems is positive, and heat input to the systems is positive. Heat input, input to the systems positive. Okay, just I will show the sign convention, sign conversion, sign convention. It will be easy actually. Let's have a check. Okay, I am taking one different new slide, blank slide. Okay, then you will understand. This is important actually. Very good questions. You have to remember. Otherwise, it will be very confusing things. Okay, suppose this is systems. I am giving some heat Q and I am getting some work W. I am getting some work. This means that the work is done by the system. Work is done by the system. So this is the positive. All are the positive. Q is entering, this is a positive, I am getting some work, good, that I am getting some work. That means, can you give some example of this scenarios? I am giving some work, I am getting some work, I am giving some heat to the system, I am getting some work.
Steam
There are
engine,
many,
we are
exactly,
supplying.
steam engine, very good. Steam engine means that this is the water, this is the water, I am giving some heat, I mean I am giving some heat energy to the steam. Steam engine means I am giving some heat energy to the steam, means water, and this steam formations will be there, and it will produce high temperature and high pressure. This high temperature and high pressure will rotate the turbine, I am getting some work. This is the positive things. Okay, the Q is positive, means that the heat is, this is the positive. Okay, the work done by the system, this is the work done by the system. So work done by the system, by the system. Next, work done from the system, sorry, work work done by the system. Next example is the, I am giving some work to the system and I am getting some heat, like hydrogen compression. Okay, this is, suppose, as I am giving work to the systems, this is, you can say, minus delta V. This is the conversion, this is nothing, you have to understand the basic things. Okay, this is the minus V. Okay, for the hydrogen compression I am giving some work, means that the work, I am giving some work, not work done by the system, I am giving some work. Okay, work required for the system to operate or to run. This is the basic sign conversions. Okay, this formula is very important. Whatever the main things that the work done for the isentropic process, it is important, work done for the isentropic process. Gamma is the specific heat ratio, gamma, for the air 1.4. Okay, for the air 1.4 NTP condition, gamma divided by gamma minus 1 RT. Okay, pressure ratio P2, higher pressure divided by lower pressure, to the power gamma minus 1 divided by gamma minus 1. Okay, this formula is very important. This formula is very important. This formula is so much important that you will get in very high competitive examinations. This formula is important. Starting from the gate, net, I don't know, set, maybe, and from the engineering perspective. Okay, this formula is important, and this is the isentropic work done. This is the isentropic work done for the case of the compressor. Obviously, work, I am giving some work, I am giving some work. Okay, I am giving some work. It is not written. Okay, I am giving some work. When you will calculate these things, when you will calculate these things, you will get minus work. When you will calculate, you will get minus work. This minus work means this minus V, suppose 100, minus work, minus 100, so minus 100. This minus 100 means that the I am giving work to the system. Okay, that is the beauty, that is the things. Otherwise, there is nothing. The sign conversion is nothing. Just you forget the sign conversions. Work, just you calculate the work done from these equations, you will get minus 100 for the compressor. Okay, but for the turbine it will different. it will positive. Okay, I will getting work, I am getting work from the turbine, the value will be positive. Okay, but hydrogen compressor, the you will get minus value. So whenever the minus value is coming, you have to that means that the minus work means that the I am giving some work to the compressor for compressing the hydrogen. Okay, this is the things. And similarly for the isentropic conditions, this was the earlier was the real situation, this is the sorry earlier was the ideal condition, this is the real gas situations work done. RT1 Z1, Z1 factor is coming, that is the compressibility factor, and P1 1 minus K1 divided by K1, P1 to the power P2, K1 minus 1 divided by P to the power K1 dP, this the formula. And this is the average, sometimes average specific heat ratio is used. Okay, sometimes specific heat ratio, because in between pressure changes there are many specific heat ratio, so we will consider one average specific heat ratio. Specific heat ratio, average specific heat ratio can be calculated by using initial plus final divided by 2, it is average situations. Okay, another process, earlier was the isentropic compression process, now is the isothermal compression process formula. Okay, this formula is also important, this formula is also important formula, isothermal process, RT V2 divided by V1. Okay, and for the van der Waals, if we consider the hydrogen gas compressions according to van der Waals equations, then this formula will be used. Okay, but this is important, VBI RT ln V2 divided by V1. Okay, compressions V1, here the for the compression process V1 is higher than the V2. Okay, V1 is higher than the V2, so just do you know that V1 is so ln will be when you will calculate the ln, V1 is higher, this is higher, this is higher, obviously the ln term will be in the minus V. Okay, are you getting me? When the work done, isothermal work done will be minus, the value will be like minus 100, you will get, if we calculate on numerical, you will get minus 100, that means you are giving work for compressing the hydrogen, because V1 is higher and V2 is lower. Okay, the denominator is higher and numerator is lesser, that means the ln value will come into the minus term. Okay, similarly for the van der Waals gas equations and compressibility, for the compressible gas equation, for the compressibility factor, if you consider this formula you have to use. There are different formula, there are two situations, one is the isothermal compression process and another one is the isentropic compression process, and for the both cases there are the real gas situations and the ideal gas situation. You have to remember the equations, or if you want to know into details, you have to go for the derivations of the work done. But actual case there are not isothermal process, neither adiabatic process, not isentropic process, it is a in between, or it is a mixture of all things. Okay, work done hydrogen compressions, but actual cases it is polytropic process, polytropic, this is called polytropic process, mixture of all things, this is a polytropic process. Polytropic process, the work done is n minus n is pv to the power n, the equations is considered pv to the power n equals to constant, that's why we will write K, we will write N in terms of K, specific heat constant. We will write N. Okay. The formula will just replace the N in terms of, in place of K. You just see the formula, N divided by N minus 1, 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 gamma divided by gamma minus 1, the same formula. Okay. For the polytropic case, for your it can be easily, you can remember these things. Okay. For the intermediate cooling systems, intermediate, this formula is used. Intermediate, I means the pressure is initial suction pressure is P1 and intermediate pressure is P2 and delivering pressure, outlet pressure is the P3. There are two steps, so you have to consider the, for the intermediate compression, isothermal compression process. This work done is the combinations of the first pressure, 1 pressure to 2 pressure, then the 2 to 3 pressure. You have to sum up these two process. And this is important, work done for the hydrogen compression. Earlier it was the state functions of the molecules. Now you can also calculate the work done for the isentropic process in terms of the, in terms of calorific value or calorific equations. Calorific equations means that the H1 minus H2. If you know the H1 minus H2, then you can easily calculate the isentropic work done. The you have not remember that the n minus 1 into r T1 P2 by P1 to the power n minus 1 divided by n minus 1. You have to not remember this bigger formula. If you know the enthalpy value, initial enthalpy value and final enthalpy value. Okay. Similarly, for the isentropic isothermal process work done, just you have to remember the H value. If you know, you can get the formula. Okay, H1 H2 minus H1 minus T H2 minus S1. This is the, in terms of calorific equations. This was the calorific equation. Earlier was the state variable function equations. Okay, earlier was the difficult. It is very, it is simple actually, but all the things are the same. If you convert this PVT into H and S, it will come this. Okay, these are the some sort of conversion process. Okay, I am going for some MCQ questions for the week number 6. Okay, starting with the first MCQ, what is the density? What is the first MCQ? What is the density of liquid hydrogen at 1 bar pressure? 1 bar pressure means that the NTP conditions. 1 bar pressure means that the NTP conditions. Okay, NTP conditions, NPT conditions, normal pressure and temperature. This is remember type questions. The value is 70.9. 70.9. Just to remember, because you have to remember these things because it is NTP conditions. NTP conditions mean, suppose you are sitting at NTP conditions. Okay, if I open one hydrogen, 1 kg hydrogen, then what is the density of this hydrogen? Okay, you should remember that the 70.9 kg per meter cube. Okay, that's why NTP conditions is important. Just you have to remember the NPT conditions. Otherwise, at suppose I will not, the questions will not come at 700 bar pressure. What is the density of the hydrogen? Okay, just okay, such that way. Second question is the operating pressure range for storing hydrogen in salt cavern are selected with reference to which of the following pressure? For the salt cavern hydrogen storage systems, is it lithostatic pressure, atmospheric pressure, hydrostatic pressure, and vacuum pressure? Operating pressure for the salt cavern hydrogen storage systems, which one is the pressure? Should be above the lithostatic pressure or atmospheric pressure or hydrostatic pressure?
Lithostatic pressure.
Lithostatic pressure. What is lithostatic pressure? Acha. Coming to the first questions, atmospheric pressure. Atmospheric pressure, so you can feel the atmospheric pressure. That means that it is surrounded by the air. It is atmospheric pressure with 1 bar atmospheric pressure. Hydrostatic pressure, when it is surrounded by the
Hydrostatic is surrounded by liquids, water.
ha, liquid or water, not water, liquid. Okay, or atmospheric means the gas, air. Okay, 1 bar. And vacuum pressure means that there is nothing, totally empty.
So below atmospheric.
No, no, no.
Yeah, vacuum
Ha,
vacuum pressure
ha,
is below atmospheric.
below atmosphere. I am coming these things in later, but initially you have to remember the vacuum pressure means that there is nothing, there is vacuum conditions. Hydrostatic pressure means that there the some pressure at surrounded by the water or below the water. Okay, and atmospheric conditions means the atmospheric air the pressure is measurement. The lithostatic pressures means that the lithostatic means that it is rock, below the rock, inside the rock, the lithostatic pressure. Okay, rock, ROCK. A vacuum means that the empty. A vacuum means that the empty means I am, suppose this is the systems. This is initially it was filled with the air. I am empty this air. I am I am taking off, taking out the air from the systems. This is empty. Obviously, the pressure will go down. Obviously, the pressure will go down. Pressure will reduce. Okay. This is the below the atmospheric pressure is called the vacuum pressure. You are you are getting you can easily connect the all the things if we if you understand the whole the cycle. Is it clear? Hello. Okay. The lithostatic pressure means it is some pressure inside the rock. Okay. Next, question number 3. Question number 3. What are depleted oil and gas reservoir? What are depleted oil and gas reservoir? Are you getting me? Okay.
The answer for question number 1 is correct. 70.9.
Question 1C. 1C is current 70.9 kg per meter cube. The unit you can see the kg per meter cube.
No,
Kg per
actually, I think it is 0.089 kg per meter cube.
0 point.
No, no. C
No,
is
no.
correct. It is for liquid hydrogen, so C is
Liquid
correct.
hydrogen. Okay,
Liquid hydrogen. Sorry,
okay.
it is liquid hydrogen. Liquid hydrogen at 1 bar pressure. Okay. And you are telling this is for the gaseous hydrogen.
gas
This is
hydrogen. Okay.
this is the gaseous hydrogen. This is the liquid hydrogen. NiQUID. This is liquid hydrogen, and this is the, I think, gas hydrogen. Okay. Question number 3: what are depleted oil and gas reservoir? Depleted oil and gas reservoir. I have told you that under the surface, when there was no coal mining, there is the storage of the natural gas, like natural gas or coal. Okay, this is the coal or natural gas. Okay, when the mines are already done, it is empty places, and hydrogen can be stored these empty places. Okay, so the carbon dioxide bearing geological capped with impermeable rock, hydrocarbon bearing geological trapped with capped impermeable rock. Obviously, the capped impermeable rock is okay. We needed, because impermeable means that there should be some rock, that impermeable rock, that hydrogen cannot be permeable easily. Okay, such that hydrogen will not scatter here and there. Okay, impermeable rock is necessary. C is the brine bearing geological trap with capped impermeable rock, hydrocarbon bearing geological trap with capped permeable rock. Which one is right? Depleted oil and gas means obviously the brine is not, brine is for the another. Okay, brine means that the salt rock, salt hydrogen storage. Carbon dioxide is not bearing. Okay, initially it was hydrocarbon, carbon, natural gas. Okay, okay, these are the in the mines of the coal, natural gas mine. So our option is B, hydrocarbon bearing geological trap with capped impermeable rock. Okay. Next, for the isothermal, for the iso isenthalpic expansion of real gas with an attractive molecules attraction, the Joule thermal coefficients is positive, negative, 0 and not defined. The question is for the isenthalpic expansion process. Isenthalpic expansion process is also called throttling process or Joule thermal expansion process. Okay. The attraction, the molecular are getting attracted. The molecular are getting attracted. In this things, the coefficient is positive. Okay, just to remember the things. This is the Joule Thomson coefficient, isothermal expansion process. This is not compression process, this is the expansion process. Okay. Question number 5. Coming to the question number 5. What will be the mass of hydrogen storage in kg? You have to calculate the M in kg. Hydrogen will compression process at a pressure P 300 bar and temperature 298 Kelvin 298 Kelvin, and volume V is 1 meter cube. You have to calculate the mass for the ideal gas, for the ideal gas, for the ideal gas, and for the real gas. Real gas. For the real gas, take Z value, compressibility factor Z equals to 1.1879. So our formula is PV for the ideal gas formula. For the ideal gas formula, PV equals to, say, PV equals to
MRT.
M RIT. Okay, so all the value are given here. All the values are given here. What is the R? What is the R value? What is the R value? What is R? Initially, you have to remember what is the R. Specific gas constant. You just remember.
8.314.
Uh, no, that's why it is specific gas constant. Okay, 8.314, it is the universal gas constant. Okay, specific gas constant value, just you search specific gas constant. What is the specific gas constant?
I think it is universal gas constant upon number of moles.
Huh. You can directly get the value also actually.
So this will be for hydrogen, correct?
No, 287 joule per kg Kelvin.
0.287. That is
Huh.
for air, correct?
That is for air, but here you can take, and that is not actually air, that is the ideal gas conditions. Okay,
Okay.
so you can put the r ri ri ri, that is the 287
287.
joule per kg Kelvin. Just can you calculate at least one ideal gas situation? Okay, can you calculate the what is the answer? You can calculate. I have not done actually. Acha, you will do in your home actually. Okay, the unit conversions you just remember, or if I get time, I will upload it in the WhatsApp group. Okay, coming to the next question. Question number 6. The compression work is maximum for which of the following process? The compression work is maximum for which of the following process? You know that the isentropic process. Question number answer D is correct. 6D. Okay. Question number 7. Question number 7. Compute isentropic compression work considering hydrogen as an ideal gas compressed from 10 to 80 bar at 298 Kelvin temperature. R is 8.314 joule per mole Kelvin, and gamma is equals to 1.4. Okay, so you have to do the write the formula. What are the given data are provided here? Temperature, R. Okay, all the things are provided to you. Okay, so here the provided, okay, the provided P1 pressure is P1 10 bar, and P2 is 80 bar, and temperature T is 298 Kelvin, and R value is 8.314 joule per mole Kelvin, and gamma value is 1.4. isentropic compression process, isentropic compression process. So the equations is work done isentropic, equations is gamma divided by 1 minus gamma R T to the power higher pressure P2 divided by P1 to the power just opposite 1 minus means the gamma minus 1 divided by gamma minus 1. Just put all the values here, you will get the answer. You just do it. Next, question number 8. Identify the correct equations for isothermal compressions work using calorific equations of state. This is the isothermal compression by using calorific state. Okay, isothermal equation for the calorific state. Calorific state is very easy. The calorific state, which one will be the correct? 1, A, B, C, D. Which one is the correct? Isothermal. Isothermal?
Third one.
No. B. 8B is correct. Third one you were saying it was, sorry, Control Z. No. Okay. Third one you were telling this is the isentropic process, isothermal process, compression process, not calorific equation. This is the
Correct.
state equation. Okay. Okay. So our answer is B. Next, question number 9. Which one of the following? Okay. Acha. First one. Which one? First one is the question number 8A. W equals to H2 minus H1. This equation is used for the isentropic work done. Isentropic work done for the calorific equation. Next one is the isothermal work done, calorific equation, and C is the isothermal work done, isothermal work done, a state equation. This is also isothermal state equation. Okay. Questions number 9. Which of the process is considered for the gas expansion process in turbine? In turbine, what happens? The steam, high temperature steam is injected to the turbine, and this high temperature steam will rotate the turbine and we will fix the generator with the turbine. We will get the electricity energy. Okay. In the turbine, the expansion process is occur. Expansion process. Obviously, high temperature steam is expanding into the turbine. Expansion. Expansion processes occur. The expansion processes occur. So our answer will be isentropic expansion process. Isentropic. Our C answer is the correct. Isentropic expansion process means that the S1 equals to S2. This is equals to S2. Delta S equals to 0. Delta S equals to 0. But throttling process, the throttling is also expansion process. But here delta H equals to 0. Sorry, delta H equals to constant. Okay, sorry, delta H equals to 0. delta equals to 0 means that the H equals to constant, H1 equals to H2. Okay. Then the last question, questions number 10, the salt caverns are developed by which method? Solution mixing, horizontal drilling, fracturing rock structure, heaping, leaching. Which one is the correct answer? The salt caverns is like below the earth surface there are some salt gather, there are salt surface. What happen? We will first drill one hole, we will put some water, inject some water, and water and salt mixture will be there, and we will out this salt and water mixture later, and the whole and the hollow portions will created on gap will be created, and finally hydrogen gas will be pushed at a high pressure for storing. So the salt caverns are developed by which method? Which one is the correct?
You think solution mining?
Solution mining. Solution mining means that the I am inputting some water and the salt is dissolving into the water, and this salt dissolve will be leaching out by using the pump just to create a hollow surface inside the rock. Okay, so this hollow surface or cave cave is developed by solution mining. Okay, solution mining means just salt and water and salt, this is the solutions, this that's why it is solution mining. Okay. Okay, this is all about week 6 lecture series discussion from my side. You just solve two numerical today. If I will get some time, I will solve and I will upload it into the WhatsApp group. And if the answer will not come, I will discuss it later. Okay. And if you have any questions or you feel any doubt from the week 6 lecture series, you can mail me or you can ask now. I will be happy to give you answer. Hello. Okay. I think we'll meet in next week. Thank you all for attending all
Thank you.
these classes or listening me. Thank you so much.